Swayam Prabha. Digital India. Educated India.
Hello everyone, in the previous class we discussed about the complete solution towards the elastic analysis of a circular tunnel. We have seen some special cases like hydrostatic state of stress and uniaxial state of stress, and how the distribution for the stresses and displacement can be derived and obtained for any particular location r comma theta. So, that we saw in detail. So, today we will learn about the analysis for the thick wall cylinder in biaxial stress field. This basically simulates the condition of a concrete lining in case of the tunnel. So, again this is an elastic analysis. So, we will have the detailed derivation with respect to the analysis for thick wall cylinder in biaxial stress field. So, as I mentioned that the application is in the problem of concrete lining of the tunnel, and to do this we consider a thick walled cylinder under uniform internal as well as external pressure. You can take a look at this figure where any point in the space can be represented by the coordinate r comma theta, as we have been discussing for the few earlier classes. Again here theta is measured from the horizontal direction in the anti-clockwise direction. The radius of the tunnel is a, and the thickness of this thick wall cylinder is b minus a. That means this outer periphery, it has a radius of b, outer circle has a radius of b. Internal pressure is being denoted by Pi. There is a negative sign associated with it, and the external pressure is denoted by minus P naught. Let us take a look at the boundary conditions. So, we have for boundary conditions sigma r at r equal to a, that is minus Pi, and tau r theta at r equal to a will be equal to 0, and sigma r at r equal to b will be minus P naught, and tau r theta at r equal to b will be equal to 0. So, these equations I mark them as 1. As we have taken earlier, this negative sign will indicate to the compression. Now, these boundary stresses, they are independent of theta. So, Airy's stress function, which was phi, can be taken as the function of r only and not the function of theta. So, in this case it is assumed that the phi can be taken by this equation 2, that is phi equal to a r square plus c log of r. These a and r, they will be determined from appropriate boundary conditions. So, what are going to be the equations of stresses in terms of phi? Let us see. These are sigma r will be equal to 1 upon r del phi del r plus 1 upon r square del 2 phi del theta 2. Just substitute this expression for phi here. So, what you will have here is 1 upon r and 2ar plus c upon r, and this is the differentiation with respect to theta, and since phi is independent of theta, so this term will become equal to 0. So, this is going to be 2a plus c upon r square, equation 3a. Then sigma theta equal to del 2 phi del r2, which is equal to say del r, and I differentiate phi once. So, that is 2ar plus c upon r, then I have to differentiate it again. So, this will be 2a minus c upon r square, that is equation 3b. Then tau r theta will be equal to 1 upon r square del phi del theta minus 1 upon r del 2 phi del r del theta, and what will be this? This will simply be equal to 0 because phi is not a function of theta. So, differentiation with respect to theta will be equal to 0. So, that is how we can obtain these equations of stresses in terms of phi. Now, substitute the boundary conditions and see what we get, that is at r equal to a, sigma r is going to be 2a plus c upon a square, that is what that we obtained just now, and this is going to be equal to minus pi, and we have tau r theta equal to 0. So, these equations will become 4a and b. Now, at r equal to b, we have sigma r as 2a plus c upon b square, which is equal to minus p naught, and tau r theta will be equal to 0. This is 5a comma 5b. Now, you just try to solve these two equations and see what we get. So, that is what c into 1 upon a square minus 1 upon b square, we can write it as p naught minus pi. Just substitute these two equations, and from here you will get c as a square b square p naught minus pi divided by b square minus a square, that is 6a. Just substitute this c in this equation and see what you will get, 2a plus b square into p naught minus pi divided by b square minus a square, and this will become equal to minus pi, and if we just solve this, this is what that we are going to get, half minus pi minus b square p naught minus pi divided by b square minus a square. Or if you further simplify this, you will get a is equal to a square pi minus b square p naught divided by 2 times b square minus a square. Make it 6b. Now, you substitute these expressions 6a and 6b in equations 3a, 3b and 3c. This is what that you are going to get, that is sigma r will be equal to a square pi minus b square p naught divided by b square minus a square plus 1 upon r square a square b square P naught minus Pi divided by B square minus A square. 7a. Sigma theta will be A square Pi minus B square P naught divided by B square minus A square minus 1 upon R square A square B square P naught minus Pi divided by B square minus A square. This is 7b, and we have seen that tau r theta will be equal to 0. So, this is equation number 7c. These sigma r and sigma theta, these are the principal stresses. These are radial and tangential, as well as these are the principal stresses. Why? Because the shear stress is 0. So, these will become principal stresses as well. Now, for the design of the lining, the critical loading condition will be when your Pi, that is the internal pressure, becomes equal to 0. So, when this becomes equal to 0, what will happen to sigma r? That will become minus B square P naught divided by B square minus A square plus 1 upon R square A square B square P naught divided by B square minus A square. That's equation 8a. And your sigma theta will be equal to minus B square P naught divided by B square minus A square minus 1 upon R square A square B square P naught divided by B square minus A square. This will become 8b. Now, what will happen at the inner periphery of the lining, at inner periphery of the lining, and what will this represent? That is when R is equal to A. Your sigma R will become equal to minus B square P naught upon B square minus A square, and see here this A square, here if you just substitute A square in place of R square, this will get cancelled out, and what you will get is B square P naught upon B square minus A square. These will get cancelled out and this will become equal to 0. 9a. And your sigma theta will be, see this is minus B square P naught upon B square minus A square, and the same thing will be here. So, I can write down simply minus 2B square P naught upon B square minus A square. That is 9b. Now, what will happen at the outer periphery of the lining, which means that when R becomes equal to B, this sigma R is going to be equal to minus P naught, that's 10a, and sigma theta will become minus P naught divided by B square minus A square into B square plus A square. This is 10b. Now, at R equal to B, that means at outer periphery of the lining, your sigma R upon minus P naught is equal to 1. Negative sign, once again, what is it? This is compressive in nature. For B by A equal to 1.25, and I take at R equal to A, your sigma theta upon minus P naught, that means this quantity, from this equation. This is going to be equal to 5.6, and at r equal to b, your sigma theta upon minus p naught will be 4.5. So let us try to draw the variation of this stress concentration factor, which is sigma upon p naught with respect to the lining thickness. Let us see how it looks like. So we have one axis, vertical axis here, and a horizontal axis. In the horizontal axis, I am drawing r upon a, which is the lining thickness, and here I have a value. I draw a vertical line corresponding to r by a equal to 1.25. That means here it is r equal to b, because we just took b by a equal to 1.25. Fine. So here it is r equal to a, that means here it is 1 and here it is 1.25. Now on the y-axis, say this is equal to 0, and I divide it into some parts, 2, 3, 4, 5 and then 6. So this is here 1, 2, 3, 4, 5 and 6. So here what we have is sigma upon p naught, which is increasing in this direction, and what do we call this as? Stress concentration factor. Now I just draw a horizontal line from this 1, and we have seen that this at r equal to b, your sigma r becomes equal to 1, and at r equal to a, this is 0. So this is how its variation is going to look like. Here it will become equal to 1. So it will be, this is going to be the variation for sigma r. And in case of the sigma theta, we have seen that at r equal to a, it is 5.6. So let us say this point is for 5.6. So I draw a line, and r equal to b, we have 4.5. So another line, let us say here this is corresponding to say 4.5. This is your 4.5. So this is like r equal to a, it is 5.6, and then it goes to 4.5 when r equal to b, that is your b by a I have considered as 1.25. So its variation will look like this. So this is the variation for sigma theta. Now let us try to draw the variation of this stress concentration factor with respect to b by a, because in this case we took b by a equal to 1.25. Now it's not necessary that always it will be 1.25. So here I have b upon a, again this is the representation of the lining thickness and increasing in this direction, and here I have sigma theta upon p naught. So I have here 1, 2, maybe this is say 3, this is 4, and here I have 5. And on this axis I have 1, 2, 3, 4, 5, 6 and 7, let us say. So this is your 7, and at b by a equal to 5, it will be, the variation is going to look like this. Something like this. So, this is what is the variation of this stress concentration factor with respect to B by A. If somebody asks you that how the variation of radial and the tangential stresses will be in case of the thick wall cylinder in biaxial stress field, this is how they will look like. Now, how to obtain the displacements? So, again, as we have seen in the previous case of the elastic analysis of the circular tunnel, in this case also this will be obtained by the integration of stress displacement equation. So, we take the situation of a plane stress, and you have seen that we have these set of equations, which is sigma r minus mu sigma theta. That is the first one. Then we have u upon r plus 1 upon v del theta is equal to 1 upon e sigma theta minus mu times sigma r. And then the last one we have as 1 upon r del u del theta plus del v del r minus v upon r is equal to 2 1 plus mu upon e into tau r theta. So, we take these as equation 11 A, B and C. Since the geometry, loading and boundary conditions, they are all symmetric with respect to theta. So, when we have the symmetry with respect to all the three situations, this is what we call as the complete symmetry. And therefore, the tangential displacements which are represented by V, this is going to be equal to 0 because of this complete symmetry. So, we get this del u del r as 1 upon e a square pi minus b square po divided by b square minus a square plus 1 upon r square a square b square p naught minus pi divided by b square minus a square minus mu upon e into a square pi minus b square p naught divided by b square minus a square minus 1 upon r square a square b square p naught minus pi divided by b square minus a square. This whole bracket will be closed. So, this is what that we are going to get for the del u del r expression. So, if we integrate it, what we can get is the expression for u. So, see how we will derive that. It will look like minus 1 upon e 1 upon r a square b square pi minus p naught divided by b square minus a square minus mu upon e 1 upon r a square b square p naught minus pi divided by b square minus a square plus 1 upon e a square pi minus b square p naught divided by b square minus a square into r minus mu upon e a square pi minus b square p naught divided by b square minus a square into r. Just solve this and you will get this expression in this form: 1 minus mu r a square pi minus b square p naught whole divided by e times b square minus a square minus 1 plus mu a square b square p naught minus pi divided by e times b square minus a square into r. This is going to be equation number 12. Now, what is the situation when we have the critical condition? So, for the critical condition, pi has to be equal to 0. So, just substitute this value of pi to equation number 12. What we will get is a nice and simple expression, which is minus b square p naught divided by e times b square minus a square 1 minus mu into r plus a square upon r 1 plus mu. This will be equation number 13. And at the internal periphery of the lining, what does this mean? What will be the value of r? This will be equal to a. So, simply this u will become minus 2a b square p naught divided by e times b square minus a square. Equation number 14. Or in a non-dimensional form, what we are going to get is u upon a will be equal to minus 2b square upon b square minus a square into p naught upon e. So, this is how we can obtain the displacement in case if we want to analyze the concrete lining in case of the circular tunnel. So, this is what is for the plane stress condition, which will be the most relevant condition in this case. So, in detail we discussed about the derivation of the stresses and displacement for the elastic analysis of the concrete lining in case of the circular tunnel. So, this is what that I wanted to discuss with you as far as the elastic analysis of the circular tunnel is concerned. In the next class, we will learn about the elastoplastic analysis of the circular tunnel. Thank you very much.